When making use of energy conservation, there is an important big picture to see. To get there, let's define our system in such a way that the conservative forces and the dissipative forces like friction are internal to the system, but the work done by other internal non-conservative forces cancel out. So there is no net work done by internal non-conservative forces, and the only net work done is done by conservative forces and dissipative forces. Any other non-conservative forces we will leave outside our system, and so they are external forces. So then this leaves us with a picture of non-conservative forces as external forces, and then all the internal forces are conservative or dissipative, or if they're non-conservative, they cancel out. Alternatively, we could instead just leave all the non-conservative forces outside our system. So we'll have all non-conservative forces be external forces, and then the conservative forces and dissipative forces be internal forces. If we do that, then we can immediately write the work kinetic energy theorem for this situation. We have the work done by our external forces, which are now all non-conservative forces, is equal to the change in kinetic energy of all the particles in our system, plus the change in potential energy of all the particles in our system, plus the change in thermal energy or internal energy of the particles of our system. This here then is the generalized work energy theorem. So it's no longer the work kinetic energy theorem, but a generalized work energy theorem where we have work done by external forces equals the change in energies of the system, where the work done by external forces changes the energy of the system in various ways. The picture we have is as follows then. We have our system, which I have boxed in, and then everything outside our system is the environment. There are external forces acting on particles inside our system, either pushing or pulling them. And then our particles inside our system exert forces on each other, and there may be dissipative forces inside our system acting on these particles too. Considering this picture then, in light of this generalized work energy theorem, the way you should think about it then is the external forces are doing work on the system to change the energy of the system. So either to add or to remove energy from the system. A way to think about it then is that there is energy being transferred from the environment to the system by the external forces, or energy being taken away from the system and being pushed to the environment, or the environment is taking away energy from the system and bringing it to the environment by doing work on the system. It's possible that the work done by the external forces are negative. In that case, you can interpret the work done as being the work being done by the system on the environment, instead of thinking of the external forces as doing work on the system by the environment. So if you have positive external work on your system, that's work done on your system by the environment. If you have negative external work done on your system, you should instead think of the system as doing work on the environment. I'm going to move this up here so that way it's near our work energy theorem equation now. Let's now also think then about what these particular terms are doing on the right-hand side of the equation, how we should interpret them. Well, we have different changes in the different energies, and these are going to be determined by their corresponding forces within our system, along with whatever external forces are acting on the particles in our system. The way you should think about it is that the internal forces are doing work inside the system to transform energy from one type to another. So we have forces acting inside our system to transform potential energy into kinetic energy and back and forth again. We have dissipative forces acting on the particles in our system to transform the kinetic energy and maybe the potential energy into thermal energy, internal energy. The forces inside our system are transforming energy from one kind of energy to another. You will see then from this equation, if there is no work done by external forces, then all these changes in energy are equal to zero. Energy is conserved. Thinking then in terms of this interpretation we are bringing to this, if there is no work being done by external forces, then there is no energy being added to our system or removed from it. Neither is our system adding energy to the environment by doing work on the environment. All the energy changes are zero. It's all contained inside our system. No energy leaves the system, no energy enters it. We call such a system an isolated system. By definition, an isolated system then is one where no energy leaves and no energy enters. If you extend our system to include more objects in it, then there will be more forces inside our system, more transformations of energy. Maybe I extend the system to include the sources of these external forces so that now they become some form of energy inside our system. And then there's no work done by external forces because all the external forces are inside our system. Imagine taking that idea and extending it to the universe. Make the system the entire universe, include the whole universe. If that's the case, then by definition, there can be no external forces because you have included every single possible thing inside the system. Well, if there are no external forces, then there can be no external work done, and therefore the sum of all these terms is going to be zero. We get energy conservation. So the universe is an isolated system. So what we see then with this big picture is to use energy conservation, it really just depends on the system you define. And if you include more objects in the system, you will eventually have a system in which energy is conserved, which in the extreme case includes everything in the whole universe. Energy is conserved in the entirety of the universe.